All right, so here's what we got going on. No class on Friday. Oop. No class on Friday. Um, Exam 3 is a week from Friday, so that's the 31st, I think. 30th? Somewhere around there. Yeah, 30th. And I thought it was mentioned last time that I haven't returned your exam 2s yet. I don't. You've taken a test in D form that because I looked for it and I have your exam 2s. Really? Okay, okay. They're graded. Oh, I'll go get them right now. Um, and the topics for exam 3 are up through stresses and beams. So we don't have class on Friday, but Monday or Wednesday next week, if you have any questions on problems related to the test, bring them to class and I'll answer them. Yep. Yeah, I mean, you'll be given, I think, every equation. Uh, I don't think there's anything in here that I want you to derive or anything. Probably, I mean, most of the stuff you need is going to be just on your calculator, the matrices and that kind of stuff. Um, and I think that is it for current events. Um, so back to what we were talking about last time. So we started macroscopic deformations. And statically indeterminate uh, structures, I guess. And we did an example where we had a column connected to the ground, and we had an upward force of 3,000 newtons and a downward force of 10,000 newtons. And we calculated the total elongation or shortening of that thing. In this case, it was shortening. I have one question about this. The basic idea is that we come up with the stresses for this due to tension and compression, and then we integrate them over the length. That's sort of the approach. Yes, but I'm getting to the question. That's the lead into the question. Um, but look at the loads that we have here. Like um, we have a fixed joint there. Here we have a point force. Here we have a point force. Um, when we're calculating the stresses due to loads like this, where do we trust the stresses that we get? Well, where don't we trust? You know, we don't trust them down here. We probably don't trust them in here somewhere, although that's a little bit of a loose interpretation of the way I described it. And we don't trust them here, right? St. Venant's principle says everywhere else we do. So the idea is there are a couple places in here, I guess. There are places where we don't trust our calculations of that stress XX. So how do we trust these integrated deformations? You know, I mean, all we're doing is taking the stresses at each location, each X value, and integrating it, basically adding up all those different deformations. I said integrated the stress. And really what we're doing is calculating the strain from that stress and then integrating that. Okay, so what do you think about that? Anyone have a smart answer?
I have an answer. I don't have an answer.
Okay. Well, the answer is we don't trust the strains at these, but as long as we have a long enough beam, the integrated, whatever those strains are going to be small. Yeah, I mean, whatever the integrated strains are is going to be small. You know, if most of your beam is stuff that you do trust, you're going to get small deformations, vanishingly small deformations in the areas you don't, and the deformations you're going to get in the parts you do trust are going to overwhelm that. And so we can sort of gloss over that fact. Okay. But it definitely is something, you know, to be aware of. I mean, because we are really taking the strains at every single point and adding them up, you know. So as long as most of the beam has, you know, trusted results, the overall elongation will be a good estimate. And I say elongation, but it's the same reason that we're going to trust our answers for flexion and twist and all that stuff. The stuff we don't trust is going to give us small answers, and it won't mess up the overall answers. Okay. Right. So there's one other way that elongation and contraction can happen. Question? Oh. Okay, don't scratch your head then. Don't get in Scott's. You don't want to be like Scott. So one other way elongation and contraction can happen. And that is thermal expansion. You might have seen this at the end of physics. If you did, you didn't spend a lot of time on it. It's not a very complicated idea. But basically, the strain due to temperature change is equal to a coefficient of thermal expansion times the change in temperature. This is a value you can look up for different materials. You know, so it has one value for steel, one value for iron, that kind of stuff. And so just the same as the idea of how we came up with macroscopic deformations due to tension compression, we calculated the strain. In that case, we started with the stress, calculated the strain, and then integrated. With this, you do it the same way, and if you integrate it, you get that delta, that's the change in length due to temperature change is equal to coefficient thermal expansion times the total length times the change in temperature. This one's actually easier to use because internal tension and compression can change over the length of the thing. Well, I suppose you could have local changes in temperature, but we're not going to deal with anything like that. So for us, we're just going to have, the whole thing's temperature goes up 50 degrees Celsius or something, and so we get a total value for the change in length. Yes?
So the idea of heating up a nut isn't that the nut expands when it gets heated, but that the length of the nut changes, therefore making the ring bigger.
Yes. So and actually I was going to say one thing about that right now. So things when the temperature increases expand uniformly. Every length dimension that you can take expands. And this is true. This is true with solids. It gets a little weird with a few materials when you go between solids and liquids, but we don't have to worry about that. So in the solid phase, if the temperature goes up, the length goes up no matter how you measure the length. So if the temperature increases, any length measurement you take increases. Okay, so for example, say that you have a cutout disc or something, okay, and you increase the temperature. You can start to get yourself sort of mixed up with this, like, oh, now if the temperature increases, there's more material here, and so maybe the outer edge goes out, but the inner edge pushes in or something. No, any length measurement you can take increases. This is a length measurement, so that inner circle increases, the outer circle increases, diameter increases, thickness increases. Okay, so it's simpler than you might be afraid that it is. Okay, so if this is the original D, this is D final. D final is greater than the initial. Okay, so let's say that we have a shape like this. where this length is 0.4 meters. This length is 0.3. Say the material has a coefficient of thermal expansion of 1.0 times 10 to the minus 5, 1 over degrees Celsius. And the temperature increases 100 degrees. And we want to calculate the change in length due to temperature change, delta T. In an engine, any of you guys have any idea how much, like, what's the change in temperature of the pistons or something once an engine warms up? Celsius or Fahrenheit? Okay. Yeah. Right. Okay. So
like the head of the pistons is like 1400 degrees. Yeah.
Okay.
Exhaust manifold.
Wow. Yeah. Okay. So we're doing this for 100 degrees, but you can imagine, I mean, in engines or, you know, various kinds of machines, you can get huge changes in temperature is all I was bringing that up for. Mm-hmm.
Like casting versus milling.
Mm-hmm. No, it's just it's a material property. Like you just look it up for steel or whatever. And so, I mean, yeah, I think if I remember right, steel's coefficient of thermal expansion is about like 1 times 10 to the minus 6 in Celsius. So if you're talking about a temperature change of, I guess it would be 500 Celsius or something, a little over that. 500 Celsius times, times 1 times 10 to the minus 6 times whatever length dimension it is, you get a pretty big percentage change in the sizes of things. And when you think of it that way, it makes sense that your car drives so weirdly before the engine warms up, you know, like. Mm-hmm. Okay. Uh-huh. Another interesting application here, I think, is so if you put like a test tube over like a Bunsen burner or something, what makes the glass crack? Well, if the whole thing was heated up exactly uniformly, there'd be no problem. The whole thing just steadily would increase in size, you know, and no issue. But if you have the fire right under one corner, that one corner is heating up a lot faster than the other stuff. And it's that mismatch in sizes that you get that causes it to crack, you know. And so the reason beakers are made out of Pyrex glass is Pyrex is made specifically to have a much lower coefficient of thermal expansion. So as if you heat a corner of Pyrex up to the same temperature, it's less likely to crack because of the mismatch in size with the surroundings. Okay, so how do we do this? I didn't give you any details about like the thickness and the thickness here and all this stuff. That's because it's easier than that. In this case, just every length dimension is going to change the same. The total length is 0.7. So the change in length due to temperature change is equal to 1 times 10 to the minus 5 times the length of 0.7. The temperature increased, so that change in temperature is positive. And you get a length change of 7.0 times 10 to the minus 4 meters. So 0.7 millimeters. And, you know, that's a pretty significant change in length, especially if you're talking about some kind of machine where parts have to mesh, you know. It wouldn't matter in this case if it's just sitting there on the table, but if you have very tight tolerances, you know, a lot of times you're machining stuff to tolerances closer than that. So that's all there is to thermal expansion. Anybody have any questions about that?
How is it related to,
I don't know. I've never heard of friction welding. Oh,
essentially, like, just take a drill bit that's not sharp on it, spin it
Mhm.
so fast when you're applying pressure that it melts a hole through by pushing
okay.
the
Mhm.
area out
Uh-huh.
after it's been heated up to a
Yeah.
temperature.
Yeah. Well, I don't know, but yeah, I'm sure that's something that you have to, in anything where you're heating up metal to a high temperature, like I'm sure that must be a very high temperature. Yeah, you'd get big changes here. So, I mean, I suppose this becomes an important effect really only when you have cases where things are being forced. You know, there's joints between things, connections between things. So maybe in that case, I mean, you would definitely get a lot of thermal expansion, but it might not be so important. You know, if you're just doing it piece by. Is it by welding? But welding tends to deal with pretty high. Yeah, that's one thing I have heard about welding. So now we're going to, so with each type of macroscopic deformation, we're going to talk about how the macroscopic deformation is calculated, and then we're going to use that for statically indeterminate systems. So here's our first statically indeterminate system. Yeah, that's a bad business model. Yeah, that's a good idea. Okay, so now we have a floor and a ceiling, and those are a fixed distance apart. Let's say that distance is 1 meter. And at the midpoint, we have a force of 20,000 newtons. And let's say that the cross-sectional area of this object is 0.01 meters squared. We want to know what are the reactions. Well, the way to do this is first we're going to go through it as a statics problem. And how do you approach it, whether it's statically determinate versus indeterminate? At the start, you don't. You treat them exactly the same. We're going to do it as a statics problem. The only thing is when we get done with the statics, we're going to see we have more variables than equations. And then we're going to use restrictions on the elongations to give us the extra equation or equations that we need. Okay, so the first step is just the statics. I'm going to turn it sideways because I'm just used to thinking about problems this way with beams. And I'm going to put the x-axis that way, the y-axis to the left. And so we have some unknown force here. That's the force at the floor. I'll call that RA. And then at the midpoint, we have a force of 20,000. And then at the other end, we're not even going to try to guess about the directions of these forces. That'll come out in the math. All right, this is RB. Everybody with me on that? That's the, it doesn't look that much like statics because we never really did statics problems this simple, but it's just a one-dimensional thing where we have two reactions and we're trying to calculate those from Newton's laws. So Newton's second law says RA minus 20,000 plus RB is equal to 0. I'll rewrite that as RA plus RB is equal to 20,000. We don't get anything from the Y equation from Newton's second law. We don't get anything from the moment equation, so this is it. We have one useful equation, two variables, and that's the definition of statically indeterminate. Okay, so what are the restrictions on the elongation of this beam, of this, I guess it's a column? Yeah, well, so this point, any point in between these two, they can move around. But we know that if we calculate the total change in length from this point to this point, that has to be 0. Okay? Because the floor and the ceiling don't go anywhere. Okay. So now we're going to use a constraint equation. That comes from the elongation or contraction. In this case, since the floor and ceiling are fixed, the total elongation, what did I call that before? U. Well, I guess I'm going to call it delta. Due to tension compression, has to be equal to 0. Okay, so what are the steps for calculating the total? And all right, so we've done a problem like this for the extension of an object before. The only difference was we had values for those two things before, right? But we're going to do it just the same way. We're going to calculate the internal loads in terms of RA and RB. See, and we're going to come up with internal loads expressed in terms of RA and RB. Then we're going to calculate the total elongation in terms of those internal loads using the equations we did before. Then we're going to set that total elongation to 0, and that'll give us a new expression in terms of these variables RA and RB. We won't introduce any new variables, just a new equation, and then we can solve it as a system. Yes? In this case, we are not going to, but it'll go into it'll cancel out. In general, yeah, you do need that. And actually, I don't think I had to give that A either. So we'll see how that cancels out, though. Okay, so let's break it up into like, call this interval 1 and this interval 2. Those are the two cuts. So cut 1 is for x values between 0 and 0.5. So the loads we have are RA. We haven't gotten to the 20,000 yet, so then we just have that internal load T. Newton's second law in the x direction says RA plus T is equal to 0. So that internal load T is equal to negative RA. And then cut 2 is for x values between 0.5 and 1. So we have RA here, the 20,000 Newton force pointing to the left, internal load T, and the x component of Newton's second law says RA minus 20,000 plus T equals 0. So T is equal to 20,000 minus RA. And now the total elongation is equal to, the formula we're going to use is T1 times L1 over EA1 plus T2 L2 over EA2. So plug in these expressions for T1 and T2. So we have negative RA times 0.5 over E times 0.01 plus the quantity 20,000 minus RA times 0.5 over E times 0.01. The total elongation is equal to 0. And so we get a bunch of cancellations. Multiply everything by 2, those go away. Multiply everything by E and 0.01, those go away. And you get the expression 20,000 minus 2RA is equal to 0. So RA is equal to 10,000. Okay, so now our system of two equations. This was our first one, call that star. This is our second one. And so based on RA being 10,000, and the two have to add up to 20,000, now we, solve the system. RA is equal to 10,000, and RB is equal to 10,000. By the way, I chose a pretty boring first example, but if that 20,000 Newton force wasn't right in the middle, if it was closer to the point A, then that 20,000, that total force of 20,000 newtons that's split between the two reaction forces would be split up differently. If that 20,000 Newton force was really close to point A, then that force point A would take up almost the whole 20,000, and the point B would have a very small load on it. So it's not always just split evenly like that. Any questions about that? I think really the bottom line with this is you don't really need to learn like a set of steps for this. You just need to remember that what you're doing is the statics first, and then you're enforcing restrictions on the elongation to come up with extra equations. And if you do that, then you can always just work your way through it. There's nothing in this that was complicated. You can think your way through it. Let's do another one. Okay, so let's say that you have a bar that has a length of 5 meters. And it was built at, 30 degrees Celsius. And we have to account for the fact that it's going to get down to negative 30 degrees Celsius. Okay, so the change in temperature is going to be equal to negative 60 degrees Celsius. I don't remember what steel's coefficient of expansion is. Okay, great. Okay, so alpha for steel is 13 times 10 to the minus 6. Yep, 1 over degree Celsius. And E is equal to 200 times 10 to the 9 pascals. And let's say that the cross-sectional area again is 0.01 meters squared. What are the reaction loads? Okay, so the idea here is that at the initial temperature, before you change the temperature, if we're ignoring the weight, there's no significant reaction load required at each one of those two walls. Okay, but when you change the temperature, this wants to shrink. And if it wants to shrink, it's going to try to pull away from those walls, and the wall is going to have to pull out on it to keep that the same length. Okay, so we're going to have that the elongation due to tension and compression plus the elongation due to thermal expansion is going to be equal to 0. Okay, so a free body diagram of this thing. The only forces applied are RA and RB. So we only need one cut. That covers the whole 5 meters. And so we have RA over here and internal tension there. And so Newton's second law in the x direction says tension is equal to negative RA. So the total elongation, just due to those reaction loads, is equal to negative RA times the length of 5 divided by the Young's modulus for steel, 200 times 10 to the 9, times 5, times the area is 0.01. And so we get 10 to the 7, 5, I can't do that. Can someone just multiply out all those numbers and give me like a coefficient for that negative RA? (2.5 times 10 to the minus 9 RA. What do we get from the statics? I sort of skipped that part, but equal and opposite, I think. RA plus RB. Yeah, so Newton's second law says RA plus RB is equal to 0. That's our equation star. And that's one equation, 2 variables. So that's when you know you have to figure out something about the elongation in order to solve this. All right, so the tension, the elongation due to the internal tension is this expression. And now we're going to figure out the elongation due to the change in temperature. So that's equal to the coefficient of thermal expansion times the length times the change in temperature, which in this case is negative 60. And what do you get for that? Negative 3.9 times 10 to the minus third. And so now our restriction says delta plus delta thermal, which is equal to negative 2.5 times 10 to the minus 9 RA minus 3.9 times 10 to the minus third has to be equal to 0 because those walls are at fixed locations. And so, what do you get for RA? Surprisingly big. 1.56 times 10 to the 6 newtons. That's our second equation. And so now solve the system. Yep, thank you. And you get RA is negative. RB is the same thing but positive. And so the loads on this are, 1.56 times 10 to the 6 newtons that way, and at the other end the other way. And so if you're trying to figure out what materials you need these walls to be made out of, or what kind of anchors you need, if you're really going to do this, you need those to be pretty substantial.
And what would be a good safety margin to negate external forces acting?
External forces like the weight, or like things that you can't, jumping up and down on it. Yeah. I think I would probably just do the redo the calculation with whatever things that you're worried about happening. But I don't really have a good answer for like the safety margin. But I think people often just add a factor of 2 onto things, or a factor of 5 onto things, and then they just figure they're good. What? That's really long, yeah. Yeah, that's true. Right.
Put a sign, don't jump like a dumbass up and down.
Yeah. Yeah, 5 meters is really long. That's
But for a beam,
13 feet. Yeah, I mean, it's across the room, less than across the room. Anybody have any other questions about that? Okay. So no class on Friday, so don't come.
So